Okay, we're going to continue with a session which deals with both Ascent and ParaView. Since some of you cannot decide if they prefer one or the other, we have the option actually to use Ascent and ParaView script. And we're going to see an example of that. Okay? And then what will be missing is an option for Conduit to use an Ascent script, but that's a long story. So what we're going to do is use Ascent to pass a Conduit node description directly to a ParaView script. So this is documented at the following link on your presentation, which I will open actually. And it's basically it's based on a ParaView plugin, which does an interpretation of the Conduit node description, and which creates the appropriate VTK object as output. So those objects at the moment are limited to VTK image data, that's the Cartesian grid, the rectilinear grid, the structured grid, which we also call curvilinear grid sometimes, or the unstructured grid. And whenever possible, of course, the data is converted to VTK using shallow copies of data array. So if we go to our documentation link here, which I need to move to this script, to this screen, there it is. And one of the demonstrations actually is with the code that I mentioned during the lunchtime. This Cloverleaf 3D code is an example where the ParaView integration is made. Basically, the way we're going to do this is to use one spatial implementation of the extract options in Ascent. And the key is right there on our screen. We're going to specify an extract command where the type is Python. And we're going to pass a ParaView script to this. So here in Python, if you use the Python type of extract, you can actually pass any other Python code which you would use to do some analysis of your data. So this is just one specific case of ParaView viz, which will intercept the Conduit data and send it to a plugin that is compiled on the ParaView side. Okay, that's important. So I have an example of it. Yeah, basically this plugin is called Ascent Source, and it's based on a feature. It's based on a set of functions in ParaView called VTK Python algorithm based. It's basically a way to create, data readers in Python, deriving from the basic Python implementation of the class, the class creating the basic VTK object. So this plugin has a fixed name, Ascent Source, and then we call it we pass to it the Ascent data. So you recognize here the standard ParaView Python code. And then there is one particularity is that we need to, on that Ascent source object, we need to update it every time the Conduit data gets updated with new data when you have a time-dependent simulation. So I'm hoping, I forgot what I put in my presentation here. Okay, so the best is to actually use I have prepared a Jupyter notebook for this, so I'm going to go to it over here. I don't know if I have one still. I'm going to restart the Jupyter notebook. It will be a few seconds, I'm hoping, not more. There we go. Okay. Projects. I don't recognize my directory structure here. Lulish Ascent. This is strange. No, I'm in the wrong place. Sorry. Examples, Lulish. There we go. So just to make sure, I'm going to recompile my Ascent. But also here I don't build. How to compile. Somebody pointed out to me that I needed to and I don't see my notebook. Wait a second. Run. Where is that? Run Lulish plus Ascent. ParaView bridge, yes. Sorry about that. Okay. Okay, we need a compilation of the code with the Ascent library. I don't know if it's there already. This is weird. Import. Run. Well, let's start by looking at the source code here in details. The Ascent plugin for ParaView is a source code element provided in the Ascent compilation. So at CSCS, based on the module Ascent, which has an environment variable called eber-root Ascent, under the example Ascent ParaView viz, there I get the source code to this Python plugin. So I get the full name of this ParaView Ascent plugin, and then I will load this plugin on line 21 here, and this is standard ParaView. This is a standard ParaView command here, load plugin, whereby we can add functionality to ParaView based on a shared library compiled elsewhere. Now, just to make it a little bit simpler, let's look at the code we already know in ParaView. We are familiar with this, the view create render view, showing the grid, selecting a variable name, coloring by that variable, getting a color transfer function, getting a color bar, etc. This is standard ParaView code. And the difference in our case here with the Ascent plugin is that we're going to use this Ascent source, update it for every time step coming in, and then save our screenshot. Also, this is standard. This is standard ParaView execution. So I'm going to now attempt to do this. I need a couple of other things. Ascent action, which is over here. And here I have a variety of things. The trigger, I want to execute this particular Python script, but at a given trigger. So I add this under this following condition, every 100 step. And this is the definition of my Ascent extract with Python. Jean-Guillaume, you were asking me earlier if it was always important to have two different YAML files, one of them specifying the trigger, one of them specifying the action. So this is the correct syntax here, but to program that, to get the right flags, it actually took me a bit of iteration. So this is the example. So we have that. The ParaView threshold is over here. I think we are familiar now with the threshold command. yeah, over here. So threshold based on my data producer, I threshold by a scalar value, a scalar variable called p between those two different numbers. This is what we will be executing. Okay. Before being able to run, I need to compile the code, so I need a terminal, because I haven't done that part, unfortunately, but this is a good exercise. So I'm going to daint examples, Lulus. I'm going to go to the instructions for compiling here, which are over here. Very good. And now I can go back to my notebook, which is this. Remove that particular directory, remove, and then as batch. So we're going to do this. We're going to create a job. Let's verify if the job has started. SQ I don't see any job, so there we go. Took a while. So now my job is there. Lulish plus Ascent plus ParaView. That's this particular job. I can look at the output of it. Hasn't started yet. I'm lost again in my Ascent. ParaView bridge. There's the output I was looking for. So I have initialized Ascent, and then every so often, every 100 iteration, I think, there we go, I am executing the Ascent code, and this telling me that there is a Tesla GPU detected. That's a good sign. It tells me that I am indeed executing something. So let's see how far it went. We're not quite done. I will look at the images, which are images of pressure threshold. If you remember the previous images we've seen of the Lulesh simulation, we have this shock wave expanding through space from the corner of the screen. And here indeed, we have just a threshold of those cells. Let's go back at the Python script. We thresholded the cells where the pressure was between 300 and 3,000 in terms of numerical value. So if I now animate this, let me stop that, or I go faster going like this. Instead of having the global volume being displayed, I only have this region of space where the pressure, as you can tell also from the column map, the pressure is limited by 3,000 as the maximum threshold. So to recapitulate, this is what we've done. We've used a special variation of the Python extract in Ascent to say, I want to execute this particular ParaView Python script every 100 iteration. This ParaView script loads the Ascent plugin, which converts the Conduit data into VTK object. And those VTK objects are then available to a standard ParaView pipeline, which we load as usual with an import ParaView. And instead of having a filter which reads data, a source of data, we have the plugin called Ascent source, which gets allocated right here. So this is the source of the data for the point of view of this visualization pipeline. We show the outline of it, and then we show the threshold. And whenever we don't specify the input to a filter or to a show command in ParaView, it means that we take the current object, as I've written over here. Since we just declared the Ascent source, this becomes the current object. So when we show it, it is the outline of the computational box. We have thresholded by this with this particular operator, and then we show the value of it. So here again, the creation of the VTK object is transparent. For you, it's a black box. You send your Conduit data to the plugin, and then the plugin does the rest. So it's a pretty nice thing to have. Let me reload those images to see. I forgot how many got displayed at the end. Okay. So we have a few more images. Now, in terms of expertise, what do you have to know? You have to know how to operate ParaView, such that ParaView writes a Python script for you. Here you notice that in my ParaView script, which is right here, I don't have any extractors anymore. Instead, I have the save screenshot command. So this is the standard ParaView code. However, that particular command is never saved into a ParaView Python script. I don't know why. If this is perhaps a suggestion we should make to the ParaView developers, because this often comes up, right? So that's the thing you would have to add to the ParaView script. So you need a little bit of expertise in using ParaView to create those particular filtering commands in ParaView, and then your conduit description of your computational nodes, this should already be acquired from the previous exercise and previous activities. So there, this is a good way to answer also a comment we had earlier: which do you prefer, the Ascent runtime or the ParaView runtime? Maybe there's an algorithm in ParaView which is the case. ParaView is a lot richer in terms of visualization algorithms implemented and available, because its base is the VTK toolkit, whereas the base engine of Ascent is VTK-M, and for the reasons I mentioned at lunchtime, VTK-M for the moment is a reduced set of visualization algorithm. So this would be a good opportunity if you wanted to use something specific to ParaView to actually have the best of both worlds. The Ascent description for triggering the pipeline, and then the execution of the ParaView on the other side. Okay, any questions so far? Are we good? I'm going to summarize if I can find a window. No? Okay, I'm over here. There we go. So we've done this. What was missing is what was missing in the notebook is the compilation of the interface, which I did via a terminal. Now, to summarize what we've done so far, we've adopted Conduit for the description of the computational simulation setup, the meshes, the variable names, the topology, coordinates, etc. All this is described via Conduit in a very intuitive, very simple manner, using, as far as possible, shared memory pointers, using zero copy pointers. So this is the base, the Conduit description of the data. Then we've fed this description to two different environments, ParaView Catalyst or Ascent. Ascent itself is written using Conduit as an API, and the visualization pipeline in Ascent is a set of triggers, queries, extractors, and scene descriptions. Whereas on the Catalyst side, the visualization pipeline is expressed via a Python code. Both of those environments, I mean, there are large development teams behind them. The US National Labs, the Kitware company is very active. There's big teams, funding. I think it's quite motivated by the Exascale effort in America. So I think there is a good future ahead of those. And we've discussed that during the breaks. There's been very recent merge requests accepted recently, both on the Catalyst side and on the Ascent side, to augment, to add more functionality to those toolkits. So those will continue to grow. ParaView itself and Ascent have demonstrated a very big strength at high scales. So this is very good. And we'll be able to use that. Now, often one of the first criticisms that people have when we present in-situ visualization is people say we're very tight with we are very, very tight with memory. The compute nodes, the GPUs have just a finite amount of memory, and we cannot afford to load more shared libraries, load more into the code. Furthermore, there's also stability questions. People say we don't want to run the risk of having a visualization library running, coexisting on the node and crashing my simulation. So there are many, there's also many criticism to that. But already 10 years ago, when I was presenting LibSync, people were telling me about this problem with memory. So we have solutions to this, and this is the last part of the presentation I want to make this afternoon, is the so-called in-transit visualization. Now, in-transit means that we're going to copy data from one location to another, and while we are copying, transiting this data, we're going to operate on it. And one of the things we can do with it is actually visualization. But it's just one special case of it. You can imagine when we talk about code coupling, coupling, for example, an atmospheric model with an ocean model for climate. Here we need to exchange data from one code to another. That's one example. But visualization is one special case of it. All right, so to do this, we're going to use Adios. And the demonstration I have is only on my laptop because on pitch day there were still missing pieces which I was not able to put together on time for the demonstration. So I'm hoping to be able to replicate all this afternoon. We're going to use Adios. Now, Adios is also quite a large package for I/O and more, and it would be difficult to give you a full appreciation for the powerful features of Adios in 20 minutes. So I have a few pointers to it in this particular slide, and I would like to invite you to look at those for more details at a later time. One thing that is important in Adios version 2.9, there's a new functionality called the plugin interface. And with the plugin interface, in the Adios language, we have engines and operators. And this plugin interface is something that allows us to program our own operators or engines into the I/O. Now, Adios by itself, I've mentioned this morning, Adios can do data compression, some data filtering, some data analysis already on the fly before saving the data to disk. And this is done independent of your compilation. So you write your interface as if you want to write your data to a disk file, and while the data is being saved, it gets transformed. Now there's a special case of the plugin interface which will enable the activation of visualization algorithms, and this is what I will demonstrate. Perhaps the short summary is over here, what ADIOS is. On this page of the documentation, a unified high-performance I/O framework to transform groups of self-describing data variables and attributes across different media, which means files, wide area networks, staging memory from one simulation code to the next. All of this is included. ADIOS is MPI based, is streaming oriented in the fact that whenever possible, things will do asynchronously with the running simulation. It's step-based in the sense that each iteration step can separate its I/O requirements into one chunk of work. It's also, like all of those other packages, free, open source, so that's really great to have. It's extreme scale by all means. I've seen examples of ADIOS being used for simulations with multiple dozens of thousands of MPI tasks. So this is really adapted for the largest computation. Now, ADIOS is just like HDF5, and in fact, ADIOS can give you the option to use HDF5 as the format to save your data. ADIOS is a description of your data, and then the raw data array being stored in binary format on your disk, but there's no convention on the internal structure of your ADIOS data. So if your data mesh is of type unstructured or rectilinear or curvilinear, you still have to add some description to the ADIOS output such that it is understood to be one particular type of mesh as opposed to another type of mesh. So this is where another layer of code will come in, and perhaps, sorry about it. Lost the page again. And that other layer is called FIDES over here on my screen. But I jumped just a bit too much ahead. Back to the previous slide. What ADIOS has, the ability to specify a specific engine called SST. And SST is this staging transport. What does that mean? It means that I can, instead of moving data and saving data to a disk file, I can make it available on a network, and then wait for a data consumer to grab that data. And this would be the classic, streaming, as I have indicated, pipe data from one simulation to the other. Now, to answer the question about what is the exact shape and form of the mesh being saved, we need a description. And this is where FIDES comes in. This is also a project that is open source. that is developed by Kitware, the same people doing ParaView and Catalyst, etc. So you can see that all the knowledge is there to make it happen. FIDES allows you to describe your mesh data with a simple JSON formatted text to indicate exactly the type of data that you are dealing with. So using this particular description, we can map, it's really what it is, map ADIOS data, map the raw data stored in ADIOS into a structure that is ready for visualization, and there are VTKM datasets. The VTKM datasets are a derivation of the VTK data object, very close but not quite. So when we read FIDES data in ParaView, we actually have a button to check convert from VTKM to VTK. We will see in the example. FIDES is available in ParaView as a reader plugin, and I will demonstrate that. The next step is this. Okay, we're going to run the simulation. This Grayscott simulator, it's a mini app which also does diffusion, simulates a diffusion process. This is an example from the ADIOS tutorial, which is also in the FIDES tutorial. And to run on my laptop, to make it simple, I've used only 4 MPI tasks. I run my executable with a particular JSON description, which is below. It has the grid resolution, here 64 cube, it's a volume. It has a number of parameters for the simulation itself. It has the name of its output, called gs.bp, and gs.bp is an ADIOS file on the disk. We will generate that data. This will be the first step in our demonstration. And then it has a configuration file in XML format, and this is typical to the ADIOS runtime. This initialization file is presented over here, and what we have to, the most important point we have to look for here is the engine type. Engine type is BP4, which in the ADIOS vocabulary means we want to write the data to disk. So it's the classic, old-fashioned, if you want, I/O. We're going to write data to disk. I'm going to execute this, and we're going to generate the file gs.bp. There is a utility command in ADIOS called bpls, and if I look at the output created with the -a option, I will look at the attributes that are saved in my ADIOS file, and I will see my a number of attributes here. My data arrays are over here. It's the U and V scalar arrays. This in ADIOS means that we have an array which is 64 cube times 100 time steps, which were saved into the field. But what is most interesting for us is those actually more than 3, 1, 2, 3, 4, 5, 6, those 6 additional parameters which are attributes which represent the data model using feeders, which represents the mesh. The mesh, the variables, the origin of space, the spacing between grid points, etc., and the association. We're very familiar with those. Those are typically the same parameters which we used earlier this morning to describe data using Conduit. When I read this data using ParaView, I will do this right now. On that directory, I will be able to visualize all 100 time steps in my output. Let me get over here. All right, 1 second. And I forgot where I installed it actually, so this is not very cool. I would look for it like this. There we go. That was easy. Over here. I'm running ParaView with the output of the simulation, which is over here. Since I run with 4 different MPI tasks, I have here 4 blocks of data. We can't see anything anymore on the screen. And if I look at, for example, a slice of this data, here an arbitrary slice, we can see the diffusion process taking place. Let me close again those things because it's I don't have control. All right. Okay, nothing new here. We've used Adios to dump data to disk. We're fine. Nothing so impressive. Oh, thank you, Jean-Guillaume. The next step is this. We're going, without recompiling the code, we're going to tell Adios to stream data to another data consumer. So we're going to use two codes running for this demo on the same compute platform, but there can be 2 different compute platforms. We're going to use an MPI exec of the data producer with a particular set of characteristics, and at the same time we're going to use MPI exec with another code the data consumer. And by the way, we don't have to use the same number of MPI tasks, which would be typical for visualization, because many visualization algorithms don't scale their communication bounds, and they don't scale very well at very high number of tasks. So it's often the case that we would want the visualization data consumer to use less tasks than the producer. What has changed here? What has changed is that in my ADIOS configuration, I've changed just one keyword. Instead of BP4, I'm now using the streaming engine, SST. And by streaming my computation from one executable to the next, this FIDES SST reader will take the data, interpret the data as VTKM objects, and run a VTKM set of visualization output. So if you look at this, this drawing I've made earlier this morning out of the, here's what we've done. We have a parallel simulation with ADIOS doing classical I/O to the disk. We can run it with ParaView, no problem there. We can switch to the streaming mode, stream it to another parallel data consumer, which executes VTKM script and which makes images of the visualization output. So this is the second step of our demonstration. And then the final step is to switch to the ParaView engine plugin. So in this case, the specification for runtime for ADIOS is, instead of using the BP4 or the SST engine, we use the plugin engine, which, as far as I know, at the moment there's only one version of it existing. It's the FIDES plugin. So this is compiled on the ADIOS side. And based on this plugin, we're going to convert the data or assimilate the data as a particular mesh type based on a JSON description. And then we're going to run a particular Python script, and then we will look at the details of those two files over here. So the GS Catalyst FIDES JSON file and the Python script. Let me pull them up. Back to my, over here. Catalyst JSON. There we go. So this is the FIDES model. It means that the source of data will be interpreted as a VTK Cartesian grid. And we have, again, just for all uniform grids, the description of the origin of the grid, the spacing of the grid, the organization of scalar fields and vector fields. And you find here a syntax that is very similar to what we've learned earlier with Conduit. This is here a JSON representation perhaps a bit more busy to read, but the same data is available. Which means that now any adios file which is interpreted based on this convention, and we're back to this principle of giving a convention of usage, any adios file based on this convention will be able to be interpreted by the script. So that's the first thing to look at, and then the second one is the Catalyst Fides Pi. Which is over here. And surprise, this looks like the ParaView Python code we learned about this afternoon. Okay, so you see we're starting to have now, we've gone through a certain learning experience, but now this is being reused over and over again. Let's look at some of the details of that. We have, of course, the creation of the view. And again, we have this trivial producer, which is the special keyword, the special object in ParaView Catalyst to tell us that we need to read the data from an incoming source. The registration name is Fides, and then the rest of it here is the standard ParaView Python code, which again we can prototype with a low resolution output. So by doing this, we're using still this particular branch of our code here, but we go directly to executing a ParaView script which will write images and save data to disk. But it's not the same data, okay? Don't compare. When I say save data, it means saving the result of visualization filters, which is usually much less data than saving the whole mesh to disk. So with a single interface, a single effort at using the adios library to encode your I/O requirements, you can do 3 different things: save data to disk, send the data via streaming to another executable, and here you have to program something using the VTKM syntax API, so it's a bit more involved as an exercise, or use directly the engine feature of adios to execute this ParaView Python code. And let me see, I think there's perhaps just a few more. No, this is what we've learned this afternoon. Yeah, we have here again the extractor, which is this way of telling ParaView we need to save images to disk at a given frequency. So here there's no frequency given, so the default would be 1. And then my standard Catalyst blueprint API is respected. I have a Catalyst execute class definition here. And basically what this does, at every step of the simulation, I will update. Update pipeline is a command we haven't seen this morning, but whenever we want to force the execution of a stage of the ParaView pipeline, we use the command update pipeline. So since this producer of data is in a waiting stage, waiting for more data to come from our live simulation, when the new data comes in, we need to trigger execution and we force it with this update pipeline. And I think that's all we have here in the code. So the moral of the story is that it's a good investment to learn this ParaView Python syntax. There's a few a few minor editing tasks which you have. The major one we've seen is to replace the reader object by this trivial producer with a registration name which fits what the data producer gives you, and then the rest of it is pretty straightforward. Here again, I have nothing about parallel execution in this Python code. This can execute on one or on n different tasks in a completely transparent manner. Now the fact is, I thought I could demonstrate that on my laptop, but there's nothing, looking at two MPI exec being executed and talking to each other, there's nothing exciting about this. What the point is that this Python script, which I create with ParaView, then gets executed directly instead of doing I/O to the disk. And that's, I think, that has a great potential for a large-scale simulation. All of this, to finalize this discussion, based on a number of parameters which you specify at runtime. So the effort of using the Adios API to write your I/O is amortized by the fact that then you have multiple ways of using the data produced by your simulation. Okay, to finish up the day, this website here, this repository remains there live even after today. I will continue to update things. We've said at the coffee break that the Python and the Fortran interface of Catalyst are now live. The VTKM version 2 interface for Ascent is live also. So I will continue to update my testing suite of demonstrations. You're welcome from time to time to look at to do a pull on this on your clone of the repo to see what other demonstrations I have put. Most of the time, I try to put things anyway which are not dedicated to PITSDate and to CSCS, so you can easily replicate those in your own compute environment. The slides are there in the slide. This is the PDF of my presentation in the slide subdirectory in the repo. The Ascent tutorial from 21 is also linked at this particular address. And with this, I'm officially closing the day. We have 10 more minutes for, actually more than that. I'm not leaving exactly at 5 o'clock. I'm not so bureaucratic, okay? So we can stay together here, get some coffee, and discuss more questions if you have them. If you come to PASC in Davos next month, I expect to have a lot more benchmarking numbers to present, because I will give a short presentation in one of the mini symposium on Tuesday. By the way, there is at PASC also one person from Kitware presenting ParaView, and I look forward to that presentation as well. There should be some new developments related to ParaView being presented at PASC. At PASC in June, I will present some of the materials that I have here with a focus based on performance and also an evaluation of the ease of development with the three different interfaces here, Ascent, Catalyst, and Adios 2. So I look forward to maybe seeing you in Davos. Okay? Good. Thanks a lot. I apologize, this morning we had this little hiccup with the notebooks until we understood that CUDA was the problem, not being able on a single node to run multiple notebooks because they each wanted a CUDA contest. But once we know that now, I think all of those demos run pretty well. On the repo, there are some files left over from last year. They're marked. You can see, you can tell because it says last updated a year ago. Don't mess with them until I clean up, until I verify that they still work with the new versions of the software I have installed on PitsDate. I forgot last year what was the level of integration we had, but it was really the beginning of this effort. So some things might not work as they did last year. What will be new, I'm hoping in the next 2 weeks, I will add to the demos that I have the stuff that relates to the new API implementation of Catalyst for Python and for Fortran. Okay? With this, you're welcome to send me private emails to discuss those in-situ questions, or more generally speaking, visualization questions so it's not my expertise in visualization is quite wide across multiple scientific fields, so perhaps there is something I can help you with for your particular needs. If you have a project at CSCS, then at the moment we will do this on PitsDate, and then the effort, as you know from talking to multiple members of our staff, the next target now is the Alps cluster. So we will do, and I will do for my part, the visualization part, all my efforts to have all those tools available on the Alps infrastructure as soon as possible. I don't know how many months this as soon as possible means. On Eiger, we have some of those tools available. The Ascent is compiled on the development cluster of Alps, which we have with the Ampere GPUs, and then the next target will be the Hopper GPUs. Soon to come. How do they say at the end of movies? Coming soon on your screen. Yes, good. Thanks a lot for your attention. Yeah, good. Thank you.